Let's answer part A. So here we have to determine marginal cost at a production level of x equals 400 calculators. So marginal cost is given by c prime of x. So this is basically the derivative of the cost function. So I'm going to find the derivative of the cost function. So the first term we have is 40x. The derivative of 40x is 40 times derivative of x is 1. So it becomes 40 times 1. And then we find the derivative of the second term, that is 0.035. Then we find the derivative of x squared, that is 2x. And the last term is a constant. Derivative of constant is 0. So it becomes a 0. Now let's simplify this. So the marginal cost function c prime of x, and this equals 40 minus 0.035 times 2 is zero point zero 0.07. This is 0.07, then times x. So this expression or this function gives the marginal cost function. Now we have to determine the marginal cost at x equal to 400. So let's replace x by 400 into the marginal cost function. So therefore this becomes c prime of 400, and this gives 40 minus zero point zero 0.07 times 400, and this equals 40 minus zero point zero 0.07 times 400 is 28. So therefore 40 minus 28 is 12. And since it is a cost, we put this in units. That is, marginal cost is dollars 12. And this answer part A. We now answer part B. So here we have to determine the marginal revenue at a production level of x equals 300 calculators. So first we determine the revenue of the given function. So we can write down this revenue as r of x, and this equals x times of the p of x, that is the demand function. So first calculate the revenue function. I'm going to substitute p of x into this expression. So therefore x times of p of x is 60 minus 0.05x. Let me distribute the x into the two terms inside the bracket. So it becomes 60 times of x is 60x, and negative 0.05 x squared. So basically this functions represents the revenue function. Now, to determine the marginal revenue, we have to find its derivative. We find the derivative of the revenue function, which gives the marginal revenue. So therefore, I write down this as r prime of x, and this is the marginal revenue function. And this equals, we find the derivative of the expression on the right side. The derivative of the first term 60x, which is 60 times the derivative of x is 1, minus zero point zero 0.05 times the derivative of x squared is 2x when we use the power rule. So let's simplify this. So this equals 60 minus zero point zero 0.05 times 2. 0.05 times 2, it is actually zero point 0.1. So I can put this as 0.1. So this equals zero point 0.1 x. Now this is the marginal revenue function in terms of x. Now we have to calculate this marginal revenue at a production level of x equal to 300. So we just have to substitute or replace x by 300. And so this gives r prime of 300. This equals 60 minus zero point 0.1 times of 300. Zero point 0.1 times of 300, and this equals 30. So therefore this becomes 60 minus 30, which is 30. So this is in terms of dollars. So we say that the marginal revenue at a production level of x equal to 300 equals $30. And this answers part B. Let's answer part C. Here we have to determine the selling price that maximizes the profit. So first we have to write the profit function. So let's write the profit function. I'm going to write down this profit as P of X, and this is the revenue function minus the cost function. So this is the formula for a profit function. Now let's replace the revenue function. Uh, we determine this revenue function in part B. I'm going to replace that. That is 60x minus of 0.05x squared minus of c of x. So it will become, we have to take the negative of the cost function. So it is negative 40x plus 0.035 x squared and negative 1250. Let's simplify this. So this implies this is the profit function p of x. Let me collect the x squared term. Here I have negative 0.05 x squared plus 0.035 x squared. So adding that, we get negative 0.015 x squared. We then have the other like terms, that is we have 60x and negative 40x, which is positive 20x. So I put positive 20x, and then finally we have the constant term, that is negative 1250. So basically this function represents the profit function. Now we have to determine the selling price that maximize the profit. So first we have to understand at what x value the profit is maximum. Notice that this profit function is a quadratic function. This is a quadratic function in terms of x variable. For any quadratic function, the maximum or minimum value occurs at negative b over 2a. So let's substitute into this formula. So basically, we are determining the x, and this equals. Let's identify the b. B is the coefficient of x, and a is the coefficient of x squared. So b is 20. So since the formula is negative b, I put this as negative b over 2 times of a is negative 0.015, and this equals this is negative 10 divided by negative 0.015. We see that these two will get cancelled, and when we plug this into the calculator, we get 10 divided by 0.015. This is approximately 666.67. 666.67. We approximate this to a whole number, that is 667. So we found that at x approximately 667 calculators, the profit is maximum. And this means we can find the corresponding selling price. To find the corresponding selling price, we have to plug in x equal to 667 into the demand function. So let's do that. So therefore, we see that the selling price that maximizes profit, this equals this P of 667. This is P of 667. Notice that this function is the demand function. It is not the profit function. So I'm using this function. So I have to replace x by 667. It is 60 minus 0.05x. So it will become 60 minus 0.05 times of x is replaced as 667. And this gives 60 minus 0.05 times 667, and this equals 33.5. So it is approximately 33. So this gives 60 minus 33, which is 27, and this has to be in dollars per item. Since it is a selling price, uh, it is in terms of dollars per item, and this answers part C.